Hello and welcome to lecture 44 of the course Theory of Computation. In the previous lecture, we saw that PCP is undecidable, right? In other words, given a PCP instance, it is undecidable to determine whether the given instance has a match. If you recall, when we learned context-free grammar in the second chapter, right, we talked about ambiguity. Right? So we say that a grammar is ambiguous if there is some string that can be derived ambiguously, meaning if there are multiple leftmost derivations for the same string, or there are multiple parse trees for the same string, right? This was the definition of ambiguity, right? We also mentioned that there are some languages, some grammars that are ambiguous. Sometimes you can remove the ambiguity from the grammar, right? Anyway, in this lecture, we are going to see an application of the fact that PCP is undecidable. So we are using the fact that PCP is undecidable to show that show the undecidability of determining whether a given grammar, a context-free grammar, is ambiguous, right? So this is not there in the textbook as a text material, but it is there as a problem 5.21. So given a CFG, it is undecidable to determine whether the given CFG is ambiguous, right? So we can also write it as a language. We can write it as a language AMBIG-CFG, as a language of all the ambiguous CFGs. And this is an undecidable language, meaning given a grammar, it's undecidable to determine whether the grammar belongs to this class. And the proof is by using a reduction from PCP. So given a PCP instance, we'll build a context-free grammar such that the context-free grammar is ambiguous if and only if the PCP instance has a match. Okay, so I'm talking about PCP. Right. So given a, let's see the reduction. The reduction itself is not that difficult to see, and even the correctness is also not that difficult to see, right? So let P be this. Okay, so where set of dominoes T1 B1 T2 B2 up to Tk Bk, where T1 B1 all come from some alphabet, right? They are strings from some alphabet. The context-free grammar is constructed as follows. Okay. The first rule is that S yields T and B. Okay, so S yields T or B. So S can give rise to T or S can give rise to T. So basically these are two branches, right? So once S derives T, then you can only use rules for T, because T never gives rise to B, right? So what are the rules? So T gives T1 TA1, where this T1 is the same as this T1 in the PCP instance. So T1 is a string, and similarly T2 capital T A2, and so on up to Tk capital T AK, right? So T1 T A1, T2 T A2 up to Tk T AK, and finally, and also T1 A1, T2 A2 up to Tk AK, this part, right, where there is no variable involved. This is one branch of computation. The other branch involves capital B, the variable B. So it's similar. So where B1 gives rise to B1 BA1, where B1 is corresponding to the B1 from the PCP instance, and I'll tell you. So A1 A2 up to AK, I'll just come back to what they are, right? B1 BA1, B2 BA2, so on up to Bk Bak. Okay, so Bk corresponds to the Bk in the PCP instance, right? So B1 corresponds to B1 here, B2 corresponds to B2 here, and so on. Everything corresponds to, so T1, T2, etc. are the strings in the PCP instance, dominoes in, right, P. And A1, A2 up to AK are all new symbols. Okay, they are not strings, they are just symbols, and they are all distinct new symbols. Maybe I should write that A1, AK are all new and distinct symbols, meaning A1 is different from A2 is different from to AK, right? So we have k new symbols a1, a2 up to ak, right? And these are the rules. S gives t or b, and once we get t, then t1 ta1 up to tk tak, then t1 a1 t2 a2 up to tk ak. Then b gives b1 ba1 up to bk bak, then b1 a1 up to bk ak, right? So these are the rules of the grammar. So the grammar is very easy to construct once we have the PCP instance, right? We don't need to check whether they are matching or anything. Now all that remains to be shown is the correctness of this reduction. So we have told given a PCP instance how to construct the grammar, right? The grammar is very easy to construct. What remains to be shown is PCP instance has a match if and only if the grammar is ambiguous. So now let's see that. Suppose the PCP instance has a match. Let us see what is the ambiguity, right? Let the match be given by repeating the dominoes or placing the I1, I2 up to IM. So I1 could be anything from 1 to k, I2 could be anything from 1 to k, and so on up to IM, right? So these are just new subscripts. So when you line up these I1th domino, I2th domino, and so on, the top string will be Ti1, Ti2 up to Tim, and the bottom string will be Bi1, Bi2 up to Bim, right? So since they are a match, it means that the top string must equal to the bottom string, right? Ti1, Ti2 up to Tim should be equal to Bi1, Bi2 up to Bim. Now we will demonstrate two derivations of the same string. So what are the derivations? First is that S gives T, and T, so we know, so we use T to give Ti1, Tai1, right? So let's say if I1 is 2, we will first give T2, Ta2, right? So if I1 is 1, it is T1, Ta1, right? And then we will use that to give Ti2, Ta2, and so on till we get, so maybe I'll just write one more step. Ti1 is already derived, then maybe Ti2, Tai2, and so on till we get Ti1, Ti2 up to Tim, followed by Aim minus 1 up to Ai2, Ai1, right? So we can get this string over here. Very similarly, we can use S gives B, B gives Bi1 gives Bi1,Bai1, and then I can use similarly Bi1, Bi2, Bai2, Ai1, right? And so on. Finally, I have Bi1, Bi2 up to Bim, Aim, Ai2, and so on, Ai2, Ai1, right? And I claim that these two strings, the underlined strings, are the same. Why is that? Because the first part, Ti1 up to Tim and Bi1 up to Bim, are the same because of the assumption that P has a match, the PCP instance has a match. So this part is the same. And the latter part is also the same because it's Aim up to Ai1 and Aim up to Ai1. This is literally the same. So this is visibly the same. Whereas for this part, we are using the fact that the PCP has a match. So we have we have one string with two derivations, and these are clearly two derivations because the first step itself is different. S gives T and S gives B. So this means that same string has two derivations. So that's the definition of the grammar being ambiguous, right? So that completes the proof that PCP has a match implies that the grammar is ambiguous. Now the reverse direction. If the grammar is ambiguous, we have to show that the PCP has a match. So let there be some string which has two derivations, right? Okay, let the string be W. Okay, let it have two derivations. Now notice the structure of the grammar here, right? Whenever we apply a rule, let's say we apply a rule, then some A1 or A2 or something gets appended towards the end of the string, right? Whichever rule, this rule or this rule or this rule or this rule, any rule where we accept the first step of the derivation where S gives T comma B, Everything else involves the creation of a A1, A2, A3, AK, something, right? One of these AIs should be produced at the end. So, because of the structure of the grammar, we may assume that the string ends with a string of A's, right? So, and these are all the A's. The A's do not come in between; they only come at the end. So, let the string of A's be AJM, AJM minus 1 up to AJ1, right? So, I am highlighting that. So, let the string let the string derived ambiguously end with AJM minus 1 up to AJ1, right? So let's write this formally. So let W be written as W prime followed by this, where W prime is free of any edges. It only consists of the original alphabet which was used to build these dominoes. So W prime only has the original alphabet, none of these A1, A2 up to AK, right? And followed by this string AJM minus 1 up to AJ1, right? Now, if any derivation ends with this, right? So now W is derived ambiguously, means the ending set of derivations, the only way that we could produce this string W, because the structure of the grammar is the following. So there are only two possibilities. One is that S gives T and T gives Tj1 T Aj1, because Aj1 has to be at the end. So this first derivation has to be this, and then it has to be Tj1 Tj2 Taj2 Aj1, right, where this has to be the next derivation and so on. Finally, we get this string Tj1 up to Tjm followed by Ajm up to Aj1. Similarly, the other derivation possible, because of the structure of the grammar, is that the ending part is Aj1, the ending symbol is Aj1. So the other possibility is S gives B and B gives Bj1 B Aj1, and again Bj1 Bj2 B Aj2 Aj1, right? And finally we get this string Bj1 up to Bjm, Ajm up to Aj1, right? So Bj1 up to Bjm and Ajm up to Aj1, right? So these are the two strings. And by assumption, this is the same string derived in two different ways, right? And we assume that Ajm up to Aj1 is a common prefix, common suffix, and that's why we got these two derivations. And this necessarily means that, so since Ajm up to Aj1 is common, the W prime part has to be this part, the first part, Tj1 up to Tjm and Bj1 up to Bjm. This means that this part is the same, right? So this part is the same. The highlighted parts has to be the same, right? Which is what I have written here. Tj1 up to Tjm is Bj1 up to Bjm, right? Now, once we have that, that is a match for the PCP instance, right? So that's a match for the PCP instance. So we first have the J1th domino, then J2th domino up to Jmth domino. So that's it. Because the grammar was ambiguous, from the ambiguity of the grammar, we got a match for the PCP instance, right? So that completes the second direction of the reduction or the correctness. So this implies that the original PCP instance P is a yes instance of PCP if and only if the grammar is ambiguous, and that gives us the reduction from the PCP to the ambiguous CFG, which means that ambiguous CFG is undecidable. In other words, given a context-free grammar, it is undecidable to determine whether it is ambiguous, right? So that is what I wanted to share in lecture 44. Given a context-free grammar, it is undecidable to determine whether it is ambiguous, and it's by a straightforward reduction from PCP. So given a PCP instance, we create a grammar. The grammar is very easy to construct, right? So we have new symbols involved, but apart from that, everything is very straightforward. S gives TB to, so 3 variables alone, starting variable S and T and B, and then we make these rules, and where T1 up to Tk, B1 up to Bk are as in the PCP instance, and A1 up to AK are new symbols. They are all distinct symbols. And we then showed that if the PCP instance has a match, which say this, then we demonstrated 2 derivations of the same string, showing ambiguity of G. Now, if G was ambiguous for the other direction, we may assume, by the structure of the grammar, the common the suffix of the string so derived could be something like AJM, AJM minus 1 up to AJ1. Once you assume that this is the suffix, the rest of the derivation is fairly is kind of constrained by the structure of the grammar, right? So the only 2 derivations possible that gives us this suffix is this as well as this, right? And that gives us that Tj1 up to Tjm is equal to Bj1 up to Bjm, which gives us a match for the PCP instance. So ambiguity implies a match and match implies an ambiguity. Hence the reduction is proper, and that gives us that gives us the reduction from PCP to ambiguous CFG. So the ambiguous CFG is undecidable, right? And that completes lecture 44. This also completes the part on computability theory, right? So this also completes, this also marks the end of computability theory, right? Which is chapter 5. So we started, computability theory was spread over 3 chapters, 3, 4 and 5. We started with defining Turing machines, types of Turing machines, just Turing thesis. Then we saw decidable languages. Then we saw undecidable languages. Then we saw that halting problem is undecidable. Then we saw reductions, which was a new way to show decidability and undecidability. Then we saw many more languages that were undecidable, right? Then we saw Rice's theorem, which was a way to show many other languages are undecidable, right? And then we saw PCP, right, which is a simple problem, which is the statement of the problem doesn't involve any Turing machines or DFAs or any such technical things. But then surprisingly, that simply stated problem was undecidable. There is no algorithmic approach to show that it is to determine whether there is a match, right? And using the fact that PCP is undecidable, we now saw that the undecidability of checking whether a given context-free grammar is ambiguous. So we saw, these are the things that we saw in computability. We saw what is decidability, what is computability. So computability means what is computable, right? So, and we saw that there are things that are not computable. We saw that there are languages that are not even Turing recognizable, right? And we saw many decidable as well as undecidable languages, right? So that completes computability theory. But however, our topics will continue. So the next lecture, we will start complexity theory, right? So there will not be, so now we'll change our change gears a bit, meaning we will no longer be interested in the nitty-gritty, or we will no longer be interested in whether it's computable, etc. Now from now on, we'll only deal with computable things, right? The languages where we are only deal with decidable things, but we will be more careful about how much resources it takes. So complexity theory is more about how much resources, how efficiently can we compute something, how much time does something take, how much space does something take, right? So basically it is going to classify problems based on resources that we need. So for all that and more, we will you can check out the next lecture, lecture number 45. And as far as lecture number 44 is concerned, this is that's all that I have. Thank you.